In this video, we're going to show how to use MATLAB to solve a second-order ordinary differential equation. To do that, we'll show how to formulate the problem in a state space formulation. That is, we'll convert one second-order ordinary differential equation to two first-order ordinary differential equations, because that is the language that MATLAB uses to solve these types of problems. We'll examine the step response of a system and show how different parameters lead to fundamentally different responses of the system. And we'll use the mass spring damper that we developed in previous videos as our example problem. To recap our mass spring damper problem, we had a mass that was supported by a spring with spring constant K and a damper with a damping coefficient that we called sigma. Now we used an automobile suspension system as the example for this derivation, and what we said is that as the road moves up and down, as you have potholes or bumps or whatever, the axle of the wheel moves with the motion u of t, and we wanted to see what the reaction of the vehicle or the mass was, and we called that x of t. The governing equation for this system was shown to be m times the second derivative of x with respect to t plus sigma times dx dt plus kx was equal to k times u plus sigma times du dt. Now for this particular problem, what we want to solve is the solution for what's known as a step response. So you could think of this as the car, if you want to think of it as a suspension system, but u is going to be 0, and then it's going to jump up to a value of 1, and then continue as a constant from there on out from all time. And what we want to see is what happens to x of t when we do this. Now, you can see we have a du dt term here on the right-hand side of the equation, and if we have a step response here in u, that du dt at that point in time would have to be infinite, and that would cause significant issues for solving this particular problem. So what we're going to do is we're going to call this jump at t equal to 0, and we're going to look at what happens to x of t for t equal to what we'll call 0 plus. So we're going to look at what happens just as the system is to the right of this jump, and when that happens, then we can conveniently ignore this du dt term because it will be 0, because u will be constant from there on out. So then, let's rewrite the equation by first dividing through by m so that our highest order derivative has no coefficient out in front of it. So we'll write the second derivative of x with respect to time plus sigma over m dx dt plus k over m x equals k over m times u. Now, as I mentioned, this is a second-order ordinary differential equation, and we need to convert it to two first-order ordinary differential equations. In general, if you have an nth-order differential equation, so an equation where we have the nth derivative, could be 5, it could be 20, it could be 2, with respect to time, plus another derivative, for example, dn minus 1x, dtn minus 1 plus ... x equals some forcing function u, where there are some coefficients, we'll call this a1, all the way up to n minus 1. We know that in general we can convert an nth order ordinary differential equation to a series of n first order differential equations. Right now we're going to concern ourselves with just second order differential equations, so we'll remove the general case. So what we'll end up with eventually are a set of equations of the form, for example, dz1 dt is equal to some coefficient times z1 plus some coefficient times z2 plus some coefficient times u, and another equation that will be the derivative of z2 with respect to time is equal to another coefficient times z1 plus our last coefficient, our final coefficient times z2 plus another coefficient times u. It may not seem obvious how to do this for a higher order or ordinary differential equation, but in general, there's a pretty straightforward procedure to accomplishing this task. And the first thing that we do is we write z1, and we just say that's going to